we're going to look at displacement reactions of halogens in this video. To do this, we need to know the displacement reaction rule, that is here in this box. The most reactive halogen always takes the cation. The cation is a positively charged ion, we'll come back to that in a moment. And we need to know the reactivity, the order of reactivity in the halogen group. Now, if we remember, the halogen group is group 7 of the periodic table. That's this group over here: fluorine, chlorine, bromine, iodine, and astatine. And the most reactive at the top, and the least reactive is at the bottom. So the order of reactivity is set by the group: most reactive, second, third, fourth, fifth. So let's write that down here. The most reactive is going to be fluorine, top of the group, then chlorine, then bromine, iodine, astatine. Okay, right. So let's apply that rule. The most reactive halogen always takes the cation. So here's an equation of for an example of a displacement reaction of halogens. Here we've got sodium iodide plus chlorine. So what we have to do to apply the rules, we have to identify the most reactive halogen, the least reactive halogen, and the cation. First off, the two halogens. We've got the iodide ion, so there's an iodine, that's a halogen. And we've got chlorine, there's another halogen. Which is more reactive? Well, chlorine is more reactive than iodine. So let's label that up. Most reactive halogen. Most reactive halogen. And this one here, this is going to be the iodine, the iodide, the least reactive halogen. And what they're fighting over is the cation. A cation is a positively charged ion, so this is the Na plus ion. When it's with the iodine, that's the I minus ion. So this is the cation here. They're fighting over the cation. They're fighting over this partner, if you like. So the rule is the most reactive halogen always takes the cation. This chlorine is going to take the sodium. That's the rule. So the product, therefore, is going to be sodium chloride, plus now the iodine's left on its own, so it's not the iodide ion anymore. The iodine's left on its own. It goes back to being the element. Iodine on its own, that loses out. Now you will see a colour change here as well. These reactions are done in solutions. This would be sodium iodide aqueous. This will be chlorine water, so chlorine dissolved in water. So these are all aqueous solutions. So we'll see a colour change because chlorine water is very, very pale green. This is colourless, transparent. This is colourless as well. So the pale green is what we start with, and it makes iodine on its own. Now, iodine solution on its own is a brown solution. Iodine in water is brown. So we'd see us change from green to brown. That's important to know. So next page, we've now got these displacement reactions to have a look at on this table here. Can we have a go at filling them in? So potassium iodide plus chlorine. So let's just go straight to simple equations. Potassium iodide. Potassium's in group 1, chlorine's in group 7. So that's a K plus ion and I minus ion. So it's the formula is Ki. Plus reacting with chlorine, Cl2. Chlorine's a diatomic molecule on its own. Now these are solutions, remember, so we'll put some state symbols in as well. Aqueous, aqueous. Now the rule, the most reactive halogen always takes the cation. What's the most reactive halogen? Chlorine. What's the cation here? The K plus. That's the cation. K plus I minus. That's the cation. The most reactive halogen takes the cation. So we end up with potassium chloride. So we're going to end up with KCl. And the iodine is going to be left all on its own. Balancing this equation now. I've got one iodine there, two iodines there. I'm going to need two of those. I've got two chlorines here. I've got one chloride there, so I'm going to need a 2 before that as well. And now the 2 Ks and the 2 Ks balance out. State symbols over here just to finish off. AQ plus AQ. They're all dissolved in water in these reactions. Next one, lithium bromide and chlorine. So let's go straight for the symbol equation. You can write the word equations in later. Lithium bromide. Lithium's group 1 of the periodic table, so Li plus is the charge on the ion. Bromine is group 7, so it's minus. So the formula there is LiBr. It's going to react with chlorine, Cl2. Again, both aqueous. Both aqueous. It's going to make, so we need to have a look at what it makes. The chlorine is more reactive than the bromine. Okay, chlorine's higher up the group than bromine. So the most reactive halogen, this one, always takes the cation. There's the cation. The Li plus is the cation. The bromide ion is the anion. So that's going to make LiCl. The chloride is going to go with the cation there. Plus, leaving on its own, bromine, leaving the less reactive halogen all on its own. State symbols again, aqueous, aqueous. And the colour change here, this was green when it was chlorine, and bromine produced as brown. These two are colourless, so the green turns to brown. If we do that reaction, you'll see green turn to brown. Next one, sodium fluoride and chlorine. Okay, so sodium is group 1 again of the periodic table, so single positive charge in the ion. The fluorine is group 7, so single negative charge, so it's a 1-to-1 ratio in that formula. Plus chlorine. Okay, which is the most reactive halogen? Well, fluorine's top of the group, so that's the most reactive halogen. Chlorine's lower down the group, that's less reactive. So the rule, most reactive halogen always takes the cation. Well, the most reactive halogen already has the cation, so no reaction. No reaction at all. Sodium bromide and iodine, NaBr plus I2. Again, the most reactive halogen always takes the cation. Well, bromine is higher up the group than iodine. Bromine already has the cation. No reaction. Last one, calcium bromide and fluorine. Calcium is in group 2 of the periodic table, so that's going to be Ca2+. Bromine, group 7, Br minus. We're going to need another bromide there, another minus, to balance out that 2+. So CaBr2. Plus fluorine, or fluorine's right at the top, so we're definitely going to get a reaction this time. The most reactive halogen takes the cation, the calcium, so it's going to make calcium fluoride. Again, fluorine's group 7, so single negative, calcium 2 positive, so we're going to need 2 fluorides. And it's going to leave the bromine all on its own, plus Br2. Okay, so you would see this one go from a very pale yellow to brown, because these salts, they are colourless. Right, now it's possible to talk about this in terms of oxidation and reduction. So let's have a look at this. We need to remember the definition for oxidation and reduction. Oxidation is loss of electrons. Reduction is gain of electrons. That's what Ulrich stands for. Oxidation, I, is L, loss of electrons. So oxidation is loss of electrons, and this is how Ulrich helps us remember. This mnemonic helps us remember. O-I-L. Oxidation is loss of electrons. Reduction, Rig, is gain of electrons. Always remember Ulrich when thinking about oxidation and reduction in terms of electrons. Well, let's have a look at what's happening in terms of gaining and losing electrons. So this is ionically bonded here. Lithium chloride, metal and a non-metal, so it's ionic. Charges, Li plus and Cl minus. The fluorine, this is covalently bonded. Covalently bonded molecules are not charged because they share electrons, so no charge here, none. Okay, lithium fluoride, ionic again. So we end up with Li plus and F minus, and the chlorine is going to be none, no charge, because that's going to be covalent again. So what we can see here is the lithium always stays positively charged, so let's not worry about that. So the Cl minus has gone to become a Cl2 molecule, so it's gone from being negatively charged to having no charge. Okay, so how does it do that? Well, electrons are negatively charged. It seems to have lost that negative charge, so it's lost the electron. Okay, so in terms of losing electrons, the Cl minus ion, which is what we've just said, has become the Cl2 molecule. So that chloride ion, the chloride ion, has lost electrons. Okay, so what therefore is being oxidized? Oxidation is loss of electrons, and we're saying the chloride ion, when it was lithium chloride, became chlorine, and chlorine is a neutrally charged molecule, so the negative charge has gone, it's been lost. Electrons are negatively charged. So what is being oxidized? Answer, the Cl minus ion. In other words, the chloride ion, to give it its full name. Now it's really important we say chloride ion, because it's not the chlorine that's being oxidized. The chlorine is a product. Okay, it's the chloride ion that is being oxidized. Right, so what else? We've got the fluorine here, the F2 molecule. This is the F2 molecule. No charge on that molecule, and that's become negatively charged. Well, how does something become negatively charged? It gains an electron. Okay, so it's gone from being neutral to being negative. Electrons are negatively charged, so it must have gained that electron to become negative. So what's gained electron? The fluorine molecule. The F2 molecule has gained that electron to become F minus. So the only way it can get to that negative charge is to gain electrons, because electrons are negative. Well, reduction is gain of electrons. The fluorine molecule. Okay, now it's important we don't say the fluoride, because the fluoride is a product. That's not gained. It's the reactant that's gained, the fluorine molecule. So write an explanation that details why displacement reactions are redox processes. Well, it's quite simple, because for this redox process to happen, this displacement reaction to happen, there has to be both oxidation and reduction. The chloride ion has to lose electrons and the fluorine molecule has to gain electrons. Okay, so displacement reactions involve one, let's say, species. When I say species, I mean one of these. One species gaining electrons, and one losing electrons. Hence, both reduction and oxidation. And the word redox is a shorthand of reduction oxidation. So that's why they're redox reactions. So there's a couple of examples down here. And to figure them out, let's do this one, the one there, the first one, that's the one we did just above. So let's do the second one. Let's put the charges on the ions here. The bromide ion has become neutral. Okay? This bromide ion has become neutral, so it was negatively charged and it goes over there and loses that negative charge. So it's losing electrons. Now, oxidation is loss of electrons, oil rig. Oxidation is loss of electrons. This is losing an electron. The bromide ion that has lost that negative charge to go over there. So the bromide ion, that's what's lost electrons. Bromide ion. Now the chlorine, this is neutral. The chlorine molecule, Cl2 molecule, that's neutral. Okay, and that's become negatively charged. That's become Cl minus. So how do we go from neutral to becoming negatively charged? We have this here would have to gain a negative charge. What's negatively charged? Electrons. Okay, so this has gained an electron. So the chlorine molecule, the Cl2 molecule. Okay, the chlorine molecule. That gains the electrons. And you can fill the last one in on your own.